with our chapter 14 review, we're going to talk about what the following are graphs. So think about the three that I've drawn here, the singular dot, this kind of V-shaped one, and this triangle with the edge. Some of them are graphs, some of them are not. Think about which would count as a graph. And this goes back to 14.1 when we learned what could be a graph and what could not be a graph. So here, would we agree that this one is not a graph because you can't just be a singular point? You also can't have just a line going to nowhere. Now this could be corrected if this also had a vertex, then it would be a graph, but you can't just have an edge going to nowhere. So these two are not graphs. And this is our only graph. Now, once we have graphs, we also talked about the idea of a simple graph. Remember, a simple graph was a graph that had no loops, which means edge going back to itself. And also it had no two vertices connected by more than one edge. So you couldn't have like more than one edge between two vertices. So you couldn't be connected by two different routes. So we've got three different graphs here. I'll give everybody a moment to write these down and think about which one of these are simple graphs. Some are, some aren't. So what do we think about this one? Simple or not simple? Let's see y'all's answers in the chat. Maybe S for simple, N for not simple. Nice, everyone so far, correct? Good job. So far I'm getting simple. What would y'all say if somebody was like, oh, but this has this curve and the curves aren't simple? That'd be kind of confusing it, right? Because a lot of times we show the curves whenever things are doubly connected, but just because something's in a curve shape doesn't mean it's a double connection, right? So the curve shape is fine. Good. The 2 points are not already connected, so they just have one connection. So this is simple. Whereas here, these 2 points, do we see they're connected by two different edges? The first one, which we can draw straight across, but then since we've already drawn it, the second one we kind of have to draw as an arc. That would make the second graph not simple. Because it's got the double connection. This one is simple. And our last one, would we agree this is not simple as well? And specifically, the troublemaker is the loop, right? We can't have loops in a simple graph.
I have a question. Okay, I know when you said no loops, but when you mean a loop, it means a loop that's going from the same vertices. Is that what you mean? Because that's like a loop, that first one.
Perfect. So the distinction is, you know, they're both curvy shapes, but in the first one, it's going from one vertex to a different one. And what makes something a loop is whenever it starts at itself and then just comes back to itself. It's not really going anywhere. So that's good. They kind of look similar, but the distinction is one goes to somewhere, one is just itself. Good question. So do we feel somewhat comfortable identifying simple graphs if we're given pictures? Okay, good. And remember, this is review time, so definitely all y'all's questions are encouraged. So we're going to count the number of edges and vertices. I'll give time for people to write that down and try to count it. And my word of caution is, remember, try to come up with a way where you can keep track of which edges you've already counted, because it'd be very easy to overcount one of them, right? Or miss one. So for these problems, I recommend you maybe check your work 2 or 3 times before you type in your answer. Perfect, Kimberly. Great job, Tiffany. So here, remember that you are allowed to bring scratch paper to the exam. That's encouraged. And it's kind of hard to trace things on the screen, right? Because you can't actually trace over it. So it is encouraged that you'd write down the graphs. Make sure you do it carefully and you don't transcribe any errors into it. But once we have it on paper, we can kind of use maybe our pencil or a highlighter to trace out, okay, this is edge 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And especially if I can trace over, it's going to be really helpful to make sure I didn't overcount and I didn't miss anything. Perfect, Selena. So we've got 12 edges, and the number of vertices I'll count similarly. So we're going to say 1, 2, 3, 4, 5, 6, 7. So there's 7 of them. And let's add a question to this. We're sometimes asked to label the degrees of a vertex. So next to each vertice, label how many degrees. Remember, the degrees are how many edges extend from one vertex. Good, that would be the sum of all of them. Great job, everyone who sent that in the chat. So for this first one here, the degree is 2 because there's 2 edges that come from that. This next one has 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4. And sometimes we were asked to find the sum of all of these, and if you added them together, we would get 24, which I found exactly right. Now, that brings us to the idea that, the number of edges is related to the sum of the degrees of all the vertices, right? Do we see that 2 times 12 gives us the sum of 24? So that was an important rule that we learned in the notes here. We learned that if you take the sum of the degrees of all the vertices and add them together, that's going to be equal to twice the number of edges. So we can use that rule to help us solve kind of these mysteries. Suppose that the sum of the degrees of a certain graph is 22. Think about how many edges that would mean we'd have to have. When you get your answer, type it in the chat. Great job, Kimberly. Perfect, Tiffany. So we know this word formula works out. We'll just fill in the pieces. What's the sum of the degrees? 22. That's equal to twice the number of edges. So we can think, what times 2 gives me 22? 11. Good. And if you wanted to, you could also divide by 2 both sides in your calculator, and you get the number of edges is 11. Great work. So now we're going to identify connected and disconnected graphs. I'll give everybody time to think about this on their own and write down if they want to. Remember, connected means from one vertex, you could eventually get to any other vertex through a sequence of edges. And let's type in the chat which one you think is connected, the first one or the second one, the connected one. Okay. Perfect, Kimberly. Perfect, Cody. Perfect, Selena. So which one is connected? Good job, Tiffany. Okay. So as I'm looking at this first one, there are definitely a lot of edges, but do y'all see, particularly if I started here, could I get over here? Remember, we can only go vertice to vertice. So I could go here, I could go here, I could go here, but then there's no way to cross, right? So this is disconnected, and you could actually imagine taking this piece that I'm highlighting in pink and just pulling it to the side, right? And they'd look completely separate. Because we know you can move things around if they're not connected. So this one's disconnected. But then this one is connected, right? Because I could go from here to here, here to here. I could reach any other location. It might take a lot of edges, but you can go from any place to any other place. So next comes the idea of isomorphic. Now remember what isomorphic was, is it told us that, you know, all the edges are doing is showing a connection, right? And it doesn't matter how long you make the edges or how short you do. All that's matter is that they're connected. It also doesn't matter if you connect them by a straight line. I could have connected these two vertices here. Instead of this straight line, I could have connected them by this little curve, right? We just often draw straight lines for efficiency. So remember that we've got a lot of flexibility in how we draw the graphs. What we care about is, are they encoding the same information? And that's the question of isomorphic. And the way you could think about that is you could either go through very carefully and check how many vertices does each graph have if they have the same continue. How many edges does each graph have if they have the same continue? Once you verify they have the same number of edges and the same number of vertices, then you would want to check the interconnectedness. Like, oh, this degree 2 is connected to a degree 3 here. Is that the same thing in the other graph? So that's one method. Or if you're a very visual person, you can probably ask yourself, is there any way I can shrink or stretch this one graph to look like this other graph? Right? Both of those work. So I'll give everybody time to think about the first two. So you're supposed to compare in the first one, this graph to this graph. And then we've got separate problem. Is this isomorphic to this? Good job, Tiffany. And remember, if you're trying to think about the deforming, you can stretch and you can shrink, but you can't cut out edges and you can't glue things together. Those are things you can't do. Do we agree to get this second one to look like the first one? I would have to imagine taking this edge and bending it and gluing it to this edge, right? So they're not isomorphic. And another way you could tell that is this is just degree 1, but everything here was degree 2. So we'd say this one's not isomorphic. Okay. However, this next one, would we agree that maybe if I just took this end and flipped it over here, it would look about right? Right? Or maybe I could alternatively take this piece and like bend it in and it would look the right. Because the only thing is the connections are the same. It's just turned around a bit and stretched a bit. So for instance, I still have 1, 2, 3, 4, 5 vertices in each. I still have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6 edges in each. I've got 2 degree 2s here, which I do here. And then I've got 2 degree 3s, which we've got there, and 1 degree 2. So we can be convinced that this one is isomorphic. And with any of these topics, if y'all would like more practice problems, just let me know and I can create more if y'all want additional practice. So any additional practice from our previous topics, or do y'all feel comfortable going forward? Good. Okay. Thanks for the feedback, everyone. So now we're going to get to the idea of our walk, path, and circuit. So a walk is the least restrictive, and I think it would be helpful for those ones on your note sheet to write out the definition of walk, path, and circuit just to keep them straight. All a walk means is that you're going through allowable edges. For instance, I could not go from A directly to E on this graph because there is no line connecting A and E, right? That would not be a walk. So walk is just stay on the edges. What a path does is it says in a path, you don't use any edge more than once. Okay. And what a circuit does is it says, okay, you don't use any edge more than once. No, I think it says vertice. Let me check that. It's one of them. So a path doesn't use an edge more than once. So it's not going to use the same edge twice or more, only one time at most. And then a circuit just improves upon that because it says, okay, you are a path, but you also have to begin and end at the same place. So all a walk is making sure that you're staying on the edges that are drawn. A path says not only are you staying on the edges, but you're not also going to repeat any edges. And then a circuit says stay on the graph, don't repeat edges, and begin and end at the same place. So of the three, circuit is the strongest. And do we see if you're a circuit, you're automatically a path and a walk? Yeah. So then we have, going back to our example, we're asked which of the following represents a walk, path, and or circuit. So look at these three and try to label it. And remember, some things have multiple labels. So if something's a walk, path, and a circuit, then you'd write down those three things. If it's just a walk, you'd write that. So think about our three descriptions given based on this graph. Remember, if you copy it to your paper, then if you can kind of trace it with your pencil, it might be easier to see and interact with. Now with path, you do not have to use every edge. That would be a Euler circuit where you're using every edge. So path, you just can't use the edge more than once. So for the first one, I just like to always trace out where I'm going. So I'm starting at A, and then it says go to B, which is fine. But then it says go to D. Is there a connection from B directly to D? No. So this is kind of saying nonsense. We can't go from B to D. So this is none. It's not a walk, it's not a path, and it's not a circuit. Now for the next one, we're starting at A again, and now I'm going straight to D. And then it says go to E. So from A to D to E, and then B to C. So do we agree that I went along allowable edges? So it is a walk. And then to check is it a path, you ask yourself, did I use any edge more than once? No, so it is a path. Now, is it a circuit? No, because it didn't begin and end in the same place, but that's right. So I'm going to say it is a walk and a path. Now for our next one, we've got A going to B, B going to C, and C going to A. Allowable edges, so it's a walk. Didn't repeat edges, so it's a path. And then do we agree since it began and in the same place, it's also a circuit? Good. Now later, in 14.2, we said, okay, we know what a walk is, we know what a path is, we know what a circuit is. Let's add an additional definition, and that's where we got to the idea of Euler and Hamilton circuits. So remember, those are special cases that add extra rules, but this is the idea just for Wolfpack and circuits. Good work, everyone. And as y'all saw in the quiz, it's kind of like a select each one, right? So you can select whichever options apply. So now let's talk about Euler circuits. Euler circuits they care about edges, and they want you to be a circuit, which means you begin and end at the same place. You don't repeat any edges, but they also want you to visit every single edge. Okay, so we need to visit every edge. We can't repeat any edges, and we have to begin and end at the same place. And there's a neat rule for knowing when something has an Euler circuit. You just have to count the degrees of every vertex. If the degree of every vertex is even, then you're guaranteed an Euler circuit. So take a moment, you've got two different graphs given. Identify which one of these would have an Euler circuit, which ones wouldn't, by counting the degrees of every vertice. Great work, Kimberly. Now, as we're counting the degrees of these vertices, if we even get one odd, that's enough to stop, right? So as I'm counting this one, I could be like, okay, this has degree 2, but this has degree 3. I don't even have to count anymore. This one does not have an Euler circuit. Even 1 is enough to make it fail. Now, as we count the next one, let's count. We've got a degree 2, degree 4, degree 2, degree 4, degree 4, degree 2, degree 2. What we really care about is all of these are even. Not necessarily what even number they are, but since they're all even, we will say it has an Euler circuit. So all we're saying is it exists. We're not necessarily finding it at this point. Next, we're asked to find an Euler circuit. So first, convince yourself that there would be one, count the degrees, make sure they're all even, and then write down one on your paper and realize there's many correct answers here, depending on where you start, what path you take, and where you end. So I could choose, we know that this is degree 2, 2, 4, 2, 2. So it definitely has one. And do we agree I could start at any of the vertices? So I'm going to write down one. Y'all might have written down a different one, but you can always check if yours is an Euler circuit, right? Trace out your path, make sure it hits every edge, but doesn't repeat itself and gets back to the same place. So I might start at A and then go to B and then go to C and then E and then D and then C and then A. Let's check if that works. A to B, B to C, C to E, E to D, D to C, C to A. So that's one example. You can check the one that you wrote down as well. And as you take the quiz from this section, 14.2, you'll see how in the quiz, they, the trouble with this is there's so many ways you could find an Euler circuit. If we're having the computer answer and I can't just check your work, I've written the problem in such a way that I've presented most of the Euler circuit, and you just have to choose the correct pieces to go in to complete the sequence. So look at the quiz so you can be familiar with the formatting before the exam. Now, remember, Euler circuit cares about edges. Hamilton circuit cares about vertices. So in this case, we are going to visit every vertex exactly one time. And we're going to end up where we started, and we do not necessarily have to use every edge. We just want to get every vertex. So if possible, find a Hamilton circuit in the first graph. If it's not possible, think about why. And if possible, find a Hamilton circuit in the second graph. Remember, you just care about visiting every edge. And Caitlin, that's correct for the last one. Great work. That's correct, Caitlin. Very nice, Kimberly. That's a good way to remember. Now as you are trying this first graph, do you see, like, if I start at A and I go to B, eventually I'll go to C. And do you see the problem is once I've passed through C, there's no way to get to the rest of the graph without passing through C again. So C kind of becomes this funnel that once you pass through, you can't get back out without repeating. That's why we'd say there's no Hamilton graph here. Now, what if I had added this additional line? Then could there be a Hamilton graph? Yeah, because I could just skirt the edges. A, B, C, E, D, A, right? Would work. Now, would there be an Euler circuit? No, right? Because at this point, if I've added one, we've got an odd degree. Does that make sense? So for the original one, as it was written, we would say there's no Hamilton circuit possible. And particularly our problem was C, because it made a funnel to which we couldn't come back out without passing again. Now take a moment to think about the second one if you haven't had a chance to. And if you found a Hamilton circuit, send it in the chat and I'll be happy to check what you send. There are many possible answers. Perfect, Caitlin. And with this one, you're not worried about hitting every edge, right? We just don't want to repeat vertices. So maybe I could start at B. Would B goes to D, goes to E, goes to C, goes to A, goes back to B work? Yeah, that's one option, right? There's many other options, but it is possible. Let's write one. The key thing is I don't want to repeat any of the interior vertices, just the beginning and end. So another one that was sent was A, B, E, A, B, E, D, C, A. That's perfect as well. Good. Great. Now, sometimes we'd be asked to describe the following. And what I mean by this is ask yourself, is this an Euler circuit or not? Is it a Hamilton circuit or not? Both those questions. Is this an Euler circuit or not? Is it a Hamilton circuit or not? For these two separate graphs. I'll give everybody time to attempt it on their own. And are y'all able to see both, or should I zoom into one and then go to the other? You can see, okay. So with the first one, do we think it's a Hamilton? I think so, right? It does visit every vertex. Let's trace it out. A goes to B, B goes to E, E goes to D, D goes to C, C goes to A. And do we see it's almost an Euler circuit, except it misses that last edge, dA. So we would have to say this is a Hamilton, but not an Euler. It is a Hamilton. Okay. And then for the next one, we'll trace it out. A goes to B, B goes to D, D goes back to B, then it goes to C, D, E, A. So is it an Euler series or circuit? Yeah, it does visit every edge exactly once. So yes to Euler, but is it a Hamilton? If it's a Hamilton, then it can't repeat vertices. I would say it's not, right? Pretty soon, A goes to B, B goes to D, and then do you see D goes back to B, so it crosses B twice pretty early on. And then also it goes back to D and uses D again. So it's not a Hamilton because it repeats vertices. But it doesn't repeat edges, which is why it's an Euler circuit. Any questions about that? Does it make sense? Okay, so we'll continue then. Identify the following are trees. This is our new information. So you've got two graphs. Identify if they're a tree or not. To remember, a tree is a connected graph without any circuits. Circuits are kind of like loops within vertices, not an actual loop, but you know what I mean.
Well, not that way. I can do it. Okay, thank you. I have a question, Ms. Wood. I'm sorry.
Yeah.
I was trying to get it before the last one. Had it not gone in those directions like they told you to do it, could it have been a Hamilton? if you just didn't use like that loop part on that last problem?
Oh yeah, I'm sure we could create a Hamilton. Now I don't know if it would still be an Euler circuit. So for instance, what if we went like A goes to B, B goes to C? Where do you think next? Maybe D, E, A?
I don't know how I had it, but yeah, I
Yeah.
didn't think, but I need to watch because if you have the directions, I need to go according to what your directions are. So.
Yeah, that's a good point. So there would be a difference in the question of is it possible versus look at this thing we're giving and assess it. It's a good question. Now, what do we think the first one is? Tree or not a tree? Good. I see a lot of shaking the heads. No, that's right. It's not a tree specifically. Do we agree this circuit is what causes it problems? Good. And then do y'all agree the second one would be a tree, right? Because it is connected and there are no circuits. And we can kind of see our phrase minimally connected because if I removed any one of these edges, it's no longer connected, right? Removing one edge disconnects it. So you can always check a tree by asking yourself, is it minimally connected? i.e., if I take away anything, would it disconnect it? Good. Now, with the tree problems, there's two types. You're given pictures and you're identifying if it's a tree or not, like what we just did. And then the next type is you're given something that's not a tree and you want to create what's called a spanning tree. So in this case, we are going to be removing edges to where we keep the vertices still connected to each other. And we don't add in any new edges, but we just take away certain ones. And here you're asked to find 3 different spanning trees for the graph. So I'll give everybody a moment, write down the basic vertices, and then connect them with the available edges, but just choose to leave off some of them to where you get a tree.
On that last problem, would that just be considered what, a connected graph? Because it's not a tree.
The one from the last page or this one that we're working on now?
I'm sorry, the last one.
Okay, let's see. I'll scroll back. Now, are you talking about this one here? Yeah, you're right. It is connected, but it's not a tree because the circuit. So we would say it's a connected graph. That is true. And we would even say it's a simple graph, right? It's meeting that requirement. It's just not a tree. Good question. Now, specifically, as we're finding the spanning tree, the idea is we still have to have a connected graph, but I'm going to at least remove something from the circuit. And could I do this? Focus in on this middle edge that I drew. That would be a no, right? I can't do that because it's not connected here. Does that make sense? So don't add any connections that aren't already there. So these two were not connected, so I can't connect them here. But I could leave the current connections and just forget one of them. So I'm going to forget this one. There we go. That could be one. Now, could I have left this one here? If you didn't see, this is the one I added back in. No, because do we agree that makes one large circuit? Good. So that's one of the three. We're supposed to draw three of them. So take a moment to draw two others on your paper. These kind of look like constellations, right? A little bit. So that might help us visualize these. Take about one more minute. And remember, the ones you draw might look different than mine, but you can assess whether you're only keeping the original connections, you're not adding anything new, and you've taken away enough edges that there's no circuits, but it's still connected. So maybe another option would have been to keep these ones. In this case, I just removed this edge here and this edge, and that kind of broke our two circuits. But I didn't add anything new. Or additionally, I could do that one. Now the way these two differ is in this case, I've removed this edge, whereas in this case, I removed this edge, but they're still different. And we could draw more as well, couldn't we? So that's the entire chapter 14 review.